Hello everyone, my name is Samwel Sekwao. I'm a quantum application scientist at INQ. Today I'm going to give you a walkthrough of SKKU challenge problem number 2, of the solutions for problem number 2 that I designed. Before I continue, I would like to thank everyone who attempted the exercises in this problem set. Thank you for attempting these problems. Let's go straight to exercise number 1. Now, quantum phase estimation, QPE, can be used to measure the Hamming weight of a quantum state and prepare a decay state. Part A of this problem, before I go any further, exercise 1 is designated as easy. Part A requires you to write down the Hamiltonian whose eigenvalues can distinguish the Hamming weight of an n-cubic quantum state. This part is worth 3 points. The answer, the Hamiltonian, is the sum from I is equal to 1 to the number of qubits, the operator I minus Z applied at qubit I, all divided by 2. Now, most people got this part right, so there are no problems there. Part B. For an n-cubic state, what is the minimum number of qubits needed to measure the Hamming weight of the state? Hint, the Hamming weight of the state is in the range 0 through n. This part is worth 2 points, and the answer is the CL of log of base 2 of n plus 1. Again, this part, most people got this one correct. Moving on to exercise number 2. The difficulty level of this exercise is medium. Now, using Qiskit, create a function that takes in the quantum state in vector format as input and returns a quantum circuit that measures the Hamming weight of this input state. Hint, there's a hint in reference 1. You can use Qiskit's initialize module to initialize the states. Exercise 2 is worth 10 points. So basically, given an input quantum state in vector format, return a quantum state that measures the Hamming weight of that state using quantum phase estimation. Now, in reference 1, there's 2 such circuits described. You could use either one of those to create this quantum circuit. Now, there is one with 0 padding and a more efficient version which does not have 0 padding. Now, answer, I created code, implement the circuit shown in figure 3 in reference 1. That is circuit without 0 padding, the more efficient one. Okay, so this is the function, Hamming weight quantum circuit. The input is a state in vector format, as I mentioned earlier. First, you're counting the number of qubits for the state. If this particular state, how many qubits does it have? This line right here, it's just log 2 times the length of the state. Log 2 of the length of the state in integer format. And then in the second step, I'm calculating the number of qubits needed for the register C. This is where you're going to make your measurements. I initialize the quantum register. And then I need also initialize the classical register. And then the quantum circuit contains both the quantum register and classical register. This step is for initializing the state. So you can use Qiskit's initialize the state. The number of the range of the qubits is qubit nk through nk plus nq. Remember, the first nk qubits are for measurement. And then the next step is to apply Hadamard's to all the qubits in the register C, the nk qubits, as you can see, and then iteratively apply control RZ and RZ gates, okay? And the final stage is, well, before the final stage, here I'm applying the inverse quantum Fourier transform to the qubits nk, including swaps, swap gates. And finally, I'm adding measurements. So I'm measuring the qubits in the register C, the first nk qubits, and the results are going to be recorded in the classical register, and then return the quantum circuit. I also wrote a helper function, get counts, which, if you run the circuit, you get a dictionary of counts, and then this literally, computes the Hamming weight and the probability of measuring that Hamming weight. So this is the quantum circuit that, given an input state in vector format, this is the function that, given an input quantum state in vector format, it returns a quantum circuit which you can run measurements on to determine the Hamming weight of the input state. Okay, that was exercise number 2. Once again, the difficulty level is medium, and it's worth 10 points. Here, you can implement either one of those two circuits, the one in figure 2 with zero padding, or the more efficient version in figure 3 without zero padding, which is what I'm showing here. Okay. Now, moving on to number 3. The difficulty level here is also medium. This has several parts. Use the function created in part 2 above. Measure the Hamming weight of the following states. In part A, the state is a 2-qubit state, as you can see, with a Hamming weight 2. This is worth 3 points. I created some code to measure the Hamming weight of the state for part A. Okay. I'm using just 100 slots for measurements. Here I'm initializing the state, and then I grab the quantum circuit from my function that I created, and then I run the circuit to get the counts. I print the counts and, calculate the Hamming weights. So as you can see here, there are the counts. You see the Hamming weight here. This is literally 2 in base, 1, 0 is 2. And then this, all of the measurements. So the only Hamming weight you can return here is 2. And that is confirmed by my helper function get counts. You can see the Hamming weight is 2 and probability is 1. Okay. Part B, the input state is 0, 1. This is also worth 3 points, this part. Again, I'm repeating the same steps as before, as in part A. 1,000 shots, the state, and then grabbing the quantum state here. Okay. And then running the quantum state, and then getting the counts, and then I print the counts and get counts. So you can see here, once I use the function I created, the Hamming weight measured is 1 with a probability of 1, which is exactly what this should happen for this state in part B here, because the Hamming weight is 1. Okay. C, the input state is a little bit complicated. It's the 0, 0 plus 1, 1 over the square root of 2. This is also worth 3 points. Now, once again, as before, get the quantum circuit. Number of shots is 10,000 here. You can use 1,000. It doesn't matter. This is the state in vector format. And then I'm grabbing the quantum state from the function that I create. No, quantum circuit from the function that I create. Run the circuit as before. Run the circuit, get the counts, and print the Hamming weights. So you can see here the Hamming weight can be 0 with a probability of 0.5, and the Hamming weight can also be 2 with a probability of 0.5. So there's a 50-50 chance of getting Hamming weight 2 or Hamming weight 0, as you can see here. The first part has Hamming weight 0, second part has Hamming weight 1. Okay. Now moving on to part D. Okay. Part D is this quantum state. It's a superposition of basis states with all of them, with each one of them with Hamming weight 2, as you can see here. This is also worth 3 points. Getting this right is worth 3 points. As before, 10,000 shots, and then I'm initializing the state. State in the vector format here, I should say. And then here, I'm getting the quantum circuit from the function that I create. Input is the state. And just like before, running the circuit, getting the counts, and printing the Hamming weight. As you can see here, the Hamming weight is 2 with a probability of 1. Now, if you look at this state here, each one of these basis states has a Hamming weight of 2. So you're only going to measure the Hamming weight of 2. And then that's why the probability is 1. So, okay. Part E. Explain the result in part C above. This is worth 3 points. Okay? As I mentioned earlier, the Hamming weight can be measured can be 0 or 2, the probability of 1/2, equal probability. If we go back to part C, this is the part C here. You can see Hamming weight can be 0. So if you measure 0, you can measure Hamming weight of 0 or Hamming weight of 2 with a probability of 1/2 in each case. Okay. So now the entire question, part 3, if I go up here, this is medium, is worth, actually it's worth 2 points each. Yeah, the entire question, part 3, is, it's 10 points. So this should be 2 points. Each one of these should be 2 points. Okay. 2 points each one of A through E, 2 points. The entire problem is 10 points. Now, exercise 4 is also designated as medium difficulty. Now, here you're supposed to explain how the function in part 2 above can be used to prepare a decay state. This is worth 10 points. Now, if you look at the circuit in part 2 above, okay, the state of the circuit after measurement is given by this equation 1 here. So after is the measured state is pk on the initial state over square root of pk, where pk is the Hamming weight projector for Hamming weight k, psi is the initial state, and pk is the probability of measuring the Hamming weight k, given by this equation here. I give as an example, for n is equal to 3, what are these Hamming weight projectors for Hamming weight k? You can see P0 is given by that, P1, P2, and P3. Basically, if you look at each one of these, each term here, it's got the basis states corresponding to Hamming weight k, these two terms here. Now, based on equation 2 here, if an initial n-qubit state has equal superposition of basis states, such as given by psi here, okay? From equation 2 above, from these projectors right here, and equation 1, from equation 2 and equation 1 above, you can clearly see that the state of the measurement after measuring Hamming weight k will be just a decay state k. So basically, if you look at equations 1 and 2, okay, the pk applied, if you measure Hamming weight 3, you just pick P3 here. So you're only choosing, decay state of N3. If you measure 2, you're measuring, if you measure Hamming weight 2, the state will be decay state N2. This is clearly seen from equations 1 and 2 here. So that's how you can use this quantum circuit to prepare decay states. Okay. Let's see. Now, moving on to exercise number 5. Now, this is designated as hard because you need to do a little bit of thinking here. Suppose we want to prepare the decay state with n is equal to 100 and k is equal to 50. So that means 100 qubits and the Hamming weight 50. What is the probability of the state will be measured? Now, this part A, what is the probability that the state will be measured? This is given 5 points. Now, the probability is n choose k over 2 to the n. How did I arrive at that? If you look at the equal superposition state, now for Hamming weight k, there are n choose k basis states with Hamming weight k. and the n-qubit quantum state has 2 to the n basis states. So after measurements, the probability of measuring, for particular n and k, the probability of measuring decay state nk is n choose k over 2 to the n. Now, for n is equal to 100 and k is equal to 50, that is 100 choose 50 over 2 to the 100, which is approximately 8%, 0.08. Okay, this part was worth 5 points. Part B. What is the minimum number of measurements required to realize such states? This is also worth 5 points. Now, given P above, the probability of measurement above, what is the minimum number of measurements required? Think of this as a geometric series. What is the expected number of measurements required to get a success for the first time? That is to measure the decay state for the first time. In such case, the probability, the number of measurements required is just 1 over P. When you do the math, you need at least 13 measurements to be able to measure one such decay state with n is equal to 100 and k is equal to 50. Okay? Now, part C, how many gates are required? This is a little involved, but it's also worth 5 points. Now, so there's two, like I mentioned earlier, there are two implementations of this circuit. There's a circuit shown in figure 2 in the reference. This has got 0 padding. There's also a circuit shown in figure 3 in the reference without 0 padding, a more efficient one. So I calculated number of gates required for either circuit because there are some people who submitted the solutions with circuit number 1, and there are others who submitted solutions with circuit number 2. So to cover everybody, I solved this problem for either case. Now let's go through this. Now the first part is for the circuit shown in figure 2 of the reference. This is the one with 0 padding. Now we have n is equal to 100, k is equal to 50. N sub k, these are the number of qubits required in the C register, which is the measurement register. This is, as we discussed earlier, is log of base 2 of n plus 1. It gives you the ceiling of log of base 2 of n plus 1. That gives you 7 if you plug in 100 there. Number of 0 padding qubits is 2 to the nk minus n plus 1. Now, if you plug in nk and n, you get 27 0 padding qubits required. And then number of Hadamard gates used in register C and state initialization. So register C, so it's Hadamard gate for each qubit, and there's nk plus n qubits. So that's 100 plus 7. So the total number of initial Hadamards is 107. Number of RZ gates used in register C. This is just RZ gates. They're all used in the qubits of register C. And there's nk qubits. Each qubits get 1 RZ gate, if you look at the circuit. So the number there is 7. And then number of control RZ gates used. Here, the number of control RZ gates is nk multiplied by nk n plus nw. If you plug in the numbers, it's 7 multiplied by 100 plus 27 for a total of 889 control RZ gates in this implementation. The implementation with this 0 padding. And then lastly, we will count the number of gates used in the inverse quantum Fourier transform circuit that is applied to register C. So it's just basically what is the number of gates needed for an inverse quantum Fourier transform on a register with nk qubits. So that is nk multiply nk plus 1 over 2 plus integer of nk over 2, which is the swap gates. Now, if you plug in nk here, which is 7, you get 31 gates for the inverse quantum Fourier transform. If you count all of the gates, you get a total of 1,034 gates for the circuit implementation with zero padding. Okay? Now, moving on to part 2. For the circuit shown in figure 3 of the reference, this is the one without zero padding. So this is more efficient. The makeup of the two circuits is almost similar except for the zero padding, without zero padding. So NK is the same, 7 as before, the number of qubits in the register C, which is the measurement register. Now, the number of Hadamard gates used in register C and state initialization. Like I mentioned, to initialize equal superposition states, you need Hadamard gates applied to 0 state qubits. So the total number of qubits needed is Nk plus N, which is 107. And then the number of RZ gates used in register C, as before, is Nk, which is 7. The number of control RZ gates used now is Nk times N. We no longer have zero padding qubits. So it's just 7 times 100, just 700. And as before, the number of gates used in inverse quantum Fourier transform applied to register C is Nk times Nk plus over 2 plus int Nk over 2, which comes out to 31. So if you count the total number of gates in this more efficient implementation, it's 845. Okay, so for part 5C, which is also worth 5 points, 1,034 gates for the inefficient implementation of the quantum circuit, and 845 gates for the efficient implementation of the quantum circuit. Now that concludes the walkthrough. Once again, I had a great time grading these problems. I really enjoyed it. And many thanks to everybody who took time to do the problems and submit the solutions. Thank you, everybody.